How we doing? I'm doing all right. Thank you for asking. What questions do you have? Things are going all right. Everybody get Everybody get the email I sent with the rubric for the proposal. All right, so you got a couple of things due on Thursday, right? You got your homework assignment due over Newton Coates quadrature, and then you've got your proposal for your final project too. You've got another deadline for progress report due a couple weeks after break, and then a couple weeks after that is when the presentations will be during celebration of scholarship. I do not expect that necessarily that you'll be completely done with everything. Okay, that's okay. Talk about for the presentation part. Talk about what you have finished and what you still need to do. I mean, if you're completely done, that's also fine. But I don't anticipate that you will be completely done with everything by the presentation. It's just a good time where everybody should be able to go get presentation. So we'll do it that way. Okay. And then your final report will be due during. If you got questions, feel free to holler at me. That's fine. I'm happy to answer. And then also don't forget that right after break, you've got your major assignment due too on that Tuesday, which also is over quadrature, just a Gaussian quadrature instead of Newton Coates. Okay. All right. Well, let's continue talking about numeric differentiation. So we're going to come up with a few other formulas today with doing numeric differentiation. We'll talk about how you can do some improvements by working off of an old formula to get better improvements of estimates as well. And then we'll switch gears a little bit, go back to integration, and talk about Monte Carlo integration, which some of you may have seen already in another class anyway, but we'll do a little bit of extensions of that. So we'll actually finish up most likely finish up Monte Carlo integration on Thursday, and that'll be the last thing we do before break. I will not give you any new assignment over break since you've got the major assignment due right after break. So I'm not going to give you anything new until after you turn that in. Sound like a plan? All right. So let's go briefly review and talk about what we talked about right at the end of class last time, where we did the forward difference approximation for your first derivative. So I'm actually writing an honest to goodness equal sign here. We know that we can approximate our first derivative using that difference formula that you talked about in Calc 1. We went through last time and showed that the truncation error part, the part that you leave off by using the difference quotient, the forward difference formula for the first derivative, the truncation error part is on the order of what the h is, right? And we went through a power series argument to show that. So let's see if we can come up with a little bit of a better approximation, perhaps. Better in the sense of that I would really like that error to be smaller by making it on the order of a higher power of h, right? If we think of h as a small number, h squared would be less than h. So if I can make the error on the order of h squared, that should be a better approximation for similar values of h than this approximation would be. All right. So one of the goals of today is just to come up with some different formulas for approximating first derivatives, second derivatives, and playing around with trying to make the order make the order of the error better. How are you?
All right. How are you?
I'm all right. Great. All right. So let's do what's referred to as the central difference formula. And let's talk about what that means. Pardon me. All right. So we called this one the forward difference. And thinking about why we call it forward difference, if I've got some function, I've got an x, and I've got an x plus h, and I'm using those 2 points. Notice I've started at the h and moved forward. All right, that's what forward difference means. Okay, and we're using basically the slope of that line, right? That was our forward difference. You could probably guess what backward difference means instead. Thoughts? Yeah, do the x minus h, right? So if you had some function, you wanted to approximate the derivative at x, and you went backward and looked at those 2 points and calculated the slope, then f of x minus h over h is the backward difference formula. Okay. So one way it looks forward, one way it looks backward. Okay. What do you think the truncation error is? This is a guess. Did we really do much of anything different by going backward than forward? No. So the truncation error in this one actually also is O of h. You can check that with the exact same power series argument we did last time. Because remember, we just plugged in the h into our power series and solved for the derivative. Well, if I put a minus h in instead of a positive h, it's literally the same computations, except that every other power of h will have a negative sign versus a positive sign. But that's not going to change anything about the truncation error. We don't worry about constants, constant multiples, I mean. Right? Okay. So that's, forward, backward, basically the same idea. One just looks forward h, one looks backward. So do you have any guesses on what the central difference might be? Where do you think you might want to put h? Or excuse me, not h. Where do you think you might want to put x? If it's called the central difference, where do you think you might want to put x? In the middle, right? All right, so your central difference formula is going to involve f of x plus h and f of x minus h. Okay? So we're going to plug both of those into our power series representation and then play with the formula so that we get play with the formula so that we can solve for f prime. That's the idea. Okay? So remember that our power series for x, pardon me. We'll center this at x naught again, like we did before. So we'll have f of x naught. I should have put x naughts everywhere, but I'm not going to worry about going back and doing that now. F of x naught, and then there's a, what? It's an f prime of x naught times x minus x naught, and f double prime of x naught over 2 x minus x naught squared. And I'll do the third one. And then an x minus, x naught cubed. Erase this so it's out of my way. Don't need it anymore. And then so on and so forth, right? Yeah. All right. So I want to do this for an f of x plus h. I want to go to the right from x, and I want to go to the left from x at x naught. Yeah, that's fine. Technically, I should be writing x naught plus h on these and x naught minus h on these because I'm going to solve for f of f prime of x naught. I got a little sloppy with my notation. It happens. All right. So when we put in x naught plus h for x, what happens to inside the parentheses for all of those, when you put in x naught plus h in for x, what do all of the expressions inside the parentheses simplify to? Just h, right? So in the first case, we'll have f of x naught plus f prime of x naught h, right? The next one will be f double prime of x naught over 2 h squared, f triple prime of x naught over 3 factorial h cubed, and so on down the line. So far, so good? Yeah? Okay. What's going to change when we do f of x naught minus h? Does the f of x naught change? Does that first term on the right-hand side change at all? No, because remember we're centering these power series at x naught. The constant has to be f of x naught on the power series, right? Remember how we created our power series? Our Taylor series in particular. Remember we were we equated function value, first derivative, second derivative, third derivative, and so on down the line, right? That was how we came up with the formula. We're trying to make, in some sense, better and better and better polynomial approximations to the function at the point. Hopefully, there is some region for which those approximations get really, really close. There's at least a little bit of interval. If there's no interval at all, then there's no point in doing the power series representation. And there are functions that do not have power series representations at a particular point that have any interval of convergence besides just the point at which you're doing the power series center, which those are useless. Okay. Shockingly enough, it's useless. If you've done, pardon me, if you've done series in general, power series in general, and used the ratio or root test to figure out the interval of convergence, you may have come up with ones that always diverged unless it was at a particular point. Those are the sucky power series. You don't want to deal with those. We want at least some interval to deal with, because the whole idea is that if I'm at a point and I want to try to get an approximation nearby, I need to be able to go nearby and figure out what the approximation is. If I don't get any type of convergence nearby, I can't do that. And so it's useless to me from a numerical standpoint. Okay. So hopefully when you do anything with power series, they at least have a tiny interval in which they converge, and then you can work with that in some sense. We're not going to do a heck of a lot with it, which is why I'm not talking about it too in depth, but I just want to talk a little bit about why I care. All right. Anyway, back to this. The constant didn't change, right? Does the next term change? Instead of plugging in x naught plus h, we're putting in x naught minus h. Does the second term change? What's it change to? A negative, right? Because you're basically the inside of the parentheses simplifies to negative h instead of positive h, right? So this one will be a minus f prime of x naught h. Does the next term change? No, because we're squaring it, right? Inside the parentheses is a minus h, but we square it. So this is going to be a plus f double prime of x naught over 2h squared. The next one will be a minus. It'll alternate, right? Every odd power of h, a negative will pop out. Every even power of h, it kills the negative, right? So far, so good? Now, on Thursday, when we developed our forward difference formula playing around with the power series, we only used the one power series expansion and then solve for f prime, right? Here I want to use both points. So I need to combine them somehow and then be able to solve for f prime. Okay? Now let's think about the name of the formula and then think about how that might inform us for what we need to do to combine these two power series. It's called the central difference formula. What do you think I might want to do with these two expressions to try to solve for f prime? Subtract them. I probably want to subtract them, right? So let's take the first one minus the second one and see what happens. So we have f of x naught, plus h minus f of x naught minus h. If I subtract these two, what happens to your f of x naughts? Cancel. And every time I say x naught, it makes me think it sound like x snot. I hear snot every time I say it. So it just amuses me. And if it's in my head, it has to be in your head now too. All right. So the f of x naughts cancel. What happens in the second term? Do they cancel? No, it's minus a minus, right? That's good news. Yeah. Okay. So that's 2 f prime of x naught over times h, sorry. How about the next two terms? Do those cancel? Those do cancel, right? And this is where we're going to get a better formula in this case in some sense. Okay. Notice that when we did this I'm going to write it on the board rather than writing it on here because I don't expect you to reproduce it. Remember when we had this last time, we had this. We only had the one formula to work with. We subtracted that over and then divided by the h. It still left an h there, right? That's how we got the old h, right? Notice in this case, it came, well, in that particular one, it came from the second derivative term. In this case, they're canceling, right? So our power on the h is going to go down on the next one, right? So in the next one, we'll get these two end up canceling. So what's that color? These two cancel, right? So we'll end up with a plus 2 f triple prime of x naught over 3 factorial h cubed. And then the fourth powers will cancel, but it doesn't really matter. I'm going to write it as a stuff with h to the n where n is greater than or equal to 5. Each term will have at least an h to the 5th in it, right? Again, why don't I care? Remember that we're trying to look at what the truncation error is and what's going to dominate the truncation error. H is thought of as being a small number. Higher powers of h get smaller, right? So we're interested in what the smallest power of h is. That tells us about the truncation error. That make sense? Okay. I know that if you've done things in computer science and talk about how many operations things take to go through, you're usually looking at the highest power, not the lowest, right? For truncation, it's the other way around. We're looking for the lowest power. Okay. It's literally the same concept. It's just flipped because you're looking at really, really small numbers rather than really, really big ones. But it literally is the same concept. Okay. All right. So now again, remember we're trying to come up with a formula for the first derivative, right? So let's solve this for the first derivative. Basically, I just need to divide by 2h, and then I've got a bunch of other junk on the end, right? Okay. So let's solve this. I'll have f prime of x naught is equal to f of x naught plus h minus f of x naught minus h all over 2h. By the way, that makes sense, hopefully, because again, what's your first interpretation of derivative? What's the geometric interpretation of derivative? how did you motivate derivatives back in Calc 1? Tangent, right? It's a slope, correct? That looks like the slope of the line from x naught minus h, f of x naught minus h, to x naught plus h, f of x naught plus h, right? It's the difference of the y's over the difference of the x's. They're 2h apart now, right? So that formula makes sense. And then we've got, I'm going to write stuff with h to the n where n is greater than or equal to, well, let's think about what the power is now. Let's think about what the power is. We had this stuff here, right? All of this stuff has at least an h cubed in it that I'm circling, doesn't it? Right? We divided by h, so all of this stuff on the end has at least what for the power of h? Squared, right? Every single term will have an h to a power where that power is at least 2. It'll go 2, 4, 6, 8, and so on, but there'll be at least a 2, right? So when we truncate, when we cancel this part out, we get something that'll be O of h squared, right? So we'll write it that way. F of x naught plus h minus f of x naught minus h all over 2h plus an O of h squared. That's a better approximation in terms of truncation error, isn't it? It should be better. We don't have to think about what happens if you had something that was on the order of h. If I wanted to make sure that I was within, say, 100, I probably need to put in 100th within my point, right? But if I wanted to within 100th and then it's O of h squared, I just need to get within a 10th. That makes it better. Sorry, I'm away. All right, it makes it better. Okay? So in some sense, this is a better approximation. What does it require, though? It requires me to have the ability to not only move forward, but backward. Okay? Some of you are in differential equations. Some of you have had differential equations. You've talked about boundary value problems. If you're on the boundary, can you always move backward or always move forward all the time? No. So from a numeric standpoint, you're not always able to move both directions. If you're on a boundary, you may not be able to. So that's why these formulas come up, and you still need them all, at least some of them. Okay. If you have a boundary value problem, you may not be able to move either backward or forward off the boundary. These formulas, by the way, are actually used in solving partial differential equations as well. You're able to do these things. All right. If you have a boundary value problem, you're going to have to either use the forward or the backward. If you don't have data that would go backward or forward, you'd have to go use one of the other formulas. You can't use the central difference because I don't have anything in the center at that point. It's okay. Actually, one of the techniques they do with partial differential equations basically is that you set up a grid of points and try to move around the grid to get to another point and keep moving through the grid, and then you use approximations off of those the function values using those pieces off the grid. It's interesting computationally. A lot of computations to go through. But partial differential equations are exceptionally applied. Lots of applications to PDEs in physics and engineering, chemistry. All right. Anyway, any questions about how we got the truncation error there? All right. Well, let's see if we can continue on and come up with other formulas, playing around with other formulas. But let's see if we can do some with the second derivative. Why not? Okay. All right. So again, pardon me, we're going to start off with our power series representation for f of x centered at an x naught. Well, we're always going to start here. I'm just rewriting it. I should just write it on the board so we can reference it there. I don't have to rewrite it every single time. But that would require forethought before I started writing. All right. So let's think a little bit about how these formulas might get created and do a little bit of a motivation rather than me just telling you, oh, here's how we're going to create our first formula. Okay? So let's think about how we just did derivatives. Our motivating geometric object for derivative is what kind of an object? What's our motivating object for derivatives? Lines, right? Because lines give us slope. Let's think back to Calc 1. The derivative gives you slope. Second derivative gives you what? First derivative you use for increasing, decreasing. Second derivative gave you. You could use it on critical points to talk about maxes and mins. So I'm thinking about for as far as the shape of the graph goes. Derivative positive tells you it went up. Derivative negative tells you it goes down. Second derivative positive tells you what? Concavity. It's bent up or down, right? Second derivative is a measure of bendiness. Technical math term. Okay? That's about how the function bends, right? Okay? A little bit. All right. So if you think about kind of the first object you learn about in algebra class, well, maybe you did circles. Let's ignore circles. First function that you did in algebra class back in high school that was bent. What's that kind of the first function that you used? Parabolas, right? That's probably the first one that was bent, right? How many points do you need to determine a parabola? 2 points determines a line. How many points do you need for a parabola? 3, right? I need 3 points. Okay. Why did I just go through all of that? Sounds like I did a review of other things. Well, I just told you that second derivative really talks about something being bent, right? So if I want to try to get an approximation for the second derivative, I'm probably trying to measure a bent thing. One of the first things that you talked about being bent with a parabola, that required 3 pieces of information. Same kind of concept here. If I want to talk about the second derivative, I need 3 pieces of information. Notice when we did first derivative, I needed 2 pieces of information, right? For the second derivative, I'm going to need 3. If you need a third derivative, you'll need 4, and so on up the line. Okay? So when we come up with a formula here for the second derivative, we're going to come up with something that has 3 pieces in it, right? So there's multiple ways that we could do that. Let's do a centered idea. Pardon me. So let's do, all right, so we've got f of x. So I'll do an f of x naught. I'll stay at the center. I'll do an f of x naught plus h. And I'll do an f of x naught minus h. We didn't do it this way, but if you were in a Calc 2 class where you derive Simpson's rule, you might have seen get the polynomial approximation on the interval from minus h to 0 to h and come up with that coefficient pattern that you get in Simpson's rule, perhaps. This is similar to that. We're starting in the middle, going a little bit to the right, going a little bit to the left, and we're going to use those 3 points to try to get us an approximation. Okay? So again, this is like a centered difference formula. It's just for the second derivative versus the first. Okay? All right, so I'm going to use these 3 pieces of information. Okay? I'm going to plug these inputs are going to get plugged into the power series. Okay? Now let's do the easy one first. If I plug x naught into the power series, what do you get out? F of x naught. So this is just that, right? my right-hand sides here are going to be, what do I get when I plug the input into the power series? Okay. Well, the input, when I plug x naught into the power series, for the power series of f centered at x naught, is just the function value. That was the whole point, right? We made the function values agree. Okay. We've done the other two. We just did the other two in the previous problem, right? So we have f of x naught plus f prime of x naught h plus f double prime of x naught over 2 h squared f triple prime of x naught over 3 factorial h cubed, and so on down the line. The only thing that changes for when we put the minus in there was that every other term is negative, right? Because we were doing a negative h to a power. These are the same power series we had in the previous example, all right? All right. All right, so let's focus first on that, the part that I just put the red box around. That's what we want to try to get an approximation for. We want to get an approximation for the second derivative, right? That's what we're gunning for. Okay. So do I want to subtract these two things? No, because they'll cancel, right? I definitely don't want to subtract. Okay, now remember, I want an approximation for the second derivative, but I want that approximation only to depend on the original function. Think about it from a computational standpoint. Think about it from a data standpoint. If you're given data, if you've collected data, all you've collected are function values, right? You don't know squat about the derivative of the function because you don't have a function given to you. You've got a bunch of data points, right? So if I want an approximation for the second derivative, I want this piece to go away. I want that to be gone, right? I don't want anything in terms of the first derivative. I want the approximation for the second derivative only to depend on the original function. Okay? What do I need to do with those expressions to make that go away? Add them, right? All right, so I need to add those things together. And in this case, let's add all three together. Okay. So we have, pardon me, f of, oops. I don't know if we need to add them all together or not. I just need to add those, let's just add those two together. Well, that's right, okay. I'll think about it, right? If we add them now, we'll get f of x naught plus h plus f of x naught minus h. And we get, oh, that's okay. That's why my brain was not working correctly. If I add those two together, these two give me a 2 f of x naught, right? In the next one, we'll just get a, what? F double prime of x naught h squared, don't we? We got a 1/2 of each of them. We agree with that? What happens to the next two? They also go away, right? So everything else that's left at the end has at least a power of 4 on the h, right? We agree with that? Yeah? Okay. So now, same idea here. Let's solve for the second derivative. If I solve for the second derivative, we need to move that over. and then divide by your h squared. So we'll have second derivative at x naught is f of x naught plus h minus 2f of x naught plus f of x naught minus h all over an h squared plus some truncation error on the end. Now remember that the truncation on the error on the end, it deals with that stuff that I wrote, right? We use that really technical stuff language, okay? Remember, when we're solving now for the second derivative, we're dividing by h squared. So instead of everything left having at least h to the fourth, everything left's going to have at least h squared, because we're going to divide out by h squared, right? So the truncation error now will be O of h squared. And notice this has a nice symmetry to what we just did for the first derivative. When we did that central difference formula for the first derivative, we got O of h squared. We've done a central difference idea here for the second derivative, and also got an O of h squared. Right? Again, what's the problem with central difference formulas? Well, again, if you're against the boundaries, you can't always get a central difference, right? Because I may not have a data point to the right of a lower bound, excuse me, to the left of a lower boundary or to the right of an upper boundary. All right? So let's see if we can come up with a formula for the second derivative that involves only points to the right, say. Okay? So going back here, I'm going to use these two, okay? Same two here. But let's say we only go to the right and I do an f of x naught plus 2h. Say I have a data point at the boundary, but I know going to the right, I have a couple more data points that I can use to approximate a second derivative. By the way, why might you want to do approximations of second derivatives? Well, from physics, heat and wave equations both have second derivatives in them, for example. Those are important equations to know. Both of those have second derivatives in them, so you might need to approximate second derivatives. Okay. All right. But again, if you're on a boundary, you might have issues, so let's see what happens. All right. Let's put in the x naught plus 2h. That doesn't change. This one does, oops, because I put in 2h for h. So you'll get a 2f prime of x naught h. Right? The next one will be 4f double prime of x naught over 2h squared. The next one will be 8f triple, f triple prime of x naught over 3 factorial h cubed, and so on down the line. So it'll be powers of 2, right? We agree? Okay. Now again, just like before, I want to solve for the second derivative. So I'm looking at these two pieces here, this one and this one, right? I don't want those to cancel. That's what I want to solve for, right? What I do want to cancel, let me erase these red lines that I put in here. What I do want to cancel is this one and this one, right? I want the f primes to go away, right? So how can I make the f prime go away with those? So I need to look at this, I need to look at this. How can I combine those to make your f prime go away? You get to multiply by constants, by the way. Yeah, I need to multiply by top one by 2 and get to subtract one way or the other, right? So let's do f of red. Let's do f of x naught plus 2h minus 2 f of x naught plus h. Try to shrink this a little bit so we can get it all on the same screen. Let's just kind of subtract down, right? Let me erase these boxes that I've got everywhere so I can just do one at a time. Okay. I've got, here's that one and this one. And we're doing 2 times the one that's at the top and subtracting it. What do you end up with for your f of x naughts? How many f of x naughts do you get? And be a negative one, right? Negative f of x naught. So I'm doing, basically I'm doing negative 2 times the first one and adding down, if you think about it that way. F primes go away, right? That was the goal, right? We were trying to get rid of the f primes. Again, why do we want to get rid of the f primes? I don't have f prime from data, right? I've got function values from data. Right? I don't want to use f prime to approximate f double prime if all I've got are function values. Right? Agree? Okay. All right. We've rigged this so that the f primes go away. So now let's look at what we have for this term and that term. I'm doing negative 2 times the top one and adding to the bottom one. What do you get? It's just f double prime of x naught over, times h squared, isn't it? Because I get a negative 1 plus a 2, right? Do you see it? When I do negative 2 times that, that cancels, right? And that is 2. Right? Now, for the last 2 examples that we did in the central difference formulas, your third derivative pieces cancel. Do they cancel this time? If I do 2 times, just shrink it just a tad more. If I do 2 times that one, negative 2 times that one, and add it to that one, does it cancel anymore? No. So now on the end, we've got stuff with h's to the ends with the n is greater than or equal to 3, all right? We didn't get that nice cancellation that we did with the central difference formulas, right? Okay. So now when we solve, we would need to add the f of x naught over and divide by h squared. Oops, I wrote the wrong thing. So you get an f of x naught plus 2h minus a 2 times f of x naught plus h plus an f of x naught, and then all over h squared. For this one now, what's your truncation error going to be? O of h to what power? The first. Why is it the first? Good. We divide by h squared. All the stuff on the end had an h cubed. So you divide by the h squared, you're left with at least an h with each of them. All right. So what's the moral of the story here? There must be a moral somewhere why we care. Well, again, the reason why we need formulas like this is because, again, if you're on the boundary, you can't always go both directions. Right? You don't always get both directions on the boundary. Okay? So when we're on the boundary, we have to go either forward or backward twice to be able to get these approximations. We lost some accuracy, right? That's kind of the moral of the story. When we're dealing with boundaries, we're going to lose some accuracy because we don't have information on both sides. We only have information on one side. Okay. Generally speaking, things around boundaries suck. There's a whole area of mathematics devoted to trying to figure out what's going on in boundaries. It's hard. Boundaries are hard in general. So you have to come up with ways to try to be clever to get around them. Because again, you're missing information. That's what makes it hard. Right. Questions on that one at all? Is it okay so far? All right. You want to do another one like these to try to come up with another formula, or you think it's okay so far? They're just all stunned. Yeah.
So, get that. Since we have n squared is 3, so it's just squared, then divided by squared.
Okay, so what would be left on that term? Okay, so of h or h squared, if h is small, which is bigger? Of h or h squared, if h is small, which is bigger? H or h squared?
H is small,
yeah.
Which is bigger?
Yeah, which is bigger?
H squared. H, you have h and then h squared.
And h is a tiny number, but yeah, the h is the h is bigger, right? So the first column is dominating. The first power is bigger than the second. Yeah. That's what it is. Yeah. There's actually, with this stuff, there's actually a little bit more technical things that's going on. Really, with power series, something referred to Taylor's theorem says that you can express what's been left off in terms of the first term that's been left off. And so that you get a constant times that first term, which has an h in it. I'm leaving that part out. There's a theoretical piece that I'm not going into too deep. It's basically an extension of the mean value theorem. The way I just want you to think about it is that I've got this whole line of things with higher and higher powers of h, but h is really small. So the thing that really matters is the smallest power of h. That's all the in-depth analysis I want you to think of as far as the truncation error goes. If you want to go deeper into that, take a higher level numerical analysis class. That'll come up. All right. Do you want to do another one like this and derive another formula? Or do you care? You want to do another one? Well, if I gave you one on the homework, do you feel confident you can come up with one, or would you like to see another one? That's what I'm asking. Thinking that you're not getting your homework after break. It's like I can do something else too. I've got another topic on this, and then Monte Carlo integration. I've got stuff I can do. I'm just asking if you want to see another example, or do you think it's okay? You want to see another example? Okay. So other things that we can do are come up with multiple point formulas for certain values. So we've done a couple of 2-point formulas for first derivatives. Let's say if we could come up with a 3-point formula for a first derivative. Okay. So let's try to, let's say we want to estimate f prime of x naught with, let's say f of x naught plus h, and f of x naught plus 2h. So I will rewrite my power series down here again just so it's on the same screen. So I've got f of x naught plus an h, will be f of x naught f prime of x naught h f double prime of x naught over 2 h squared triple prime over 3 factorial h cubed, and so on down the line. Same exact expansion that we had before, right? And then let's do x naught plus 2h. By the way, there's a whole list of these formulas in the book. I'm just picking one. It's just, you can come up with them out of the book. It's on page 511 of your book if you're interested. There's 510 and 511. You can see my hard copy of the book was a 3-hole punch, which is why I just pull pages out when I bring it to class. Okay. All right. F prime. Sorry, it's a 2f prime of x naught h, a 4 f double prime of x naught over 2 h squared, and 8. Why do I keep forgetting the f when I write the 8? Triple prime of x naught over 3 factorial h cubed, and so on. Okay. What's the point of using extra points? Okay. So let's, again, this would be a type of problem where you've got information going to the right, but not anything to the left of x naught. This would be an example of something where you might want to use this type of a formula. All right? If I want to go x naught plus h, x naught plus 2h, when I don't have anything to the left of x naught, then we want to go this direction. Why would I want to use 3 points rather than 2? We have 2-point formulas. Why wouldn't I just do a 2-point formula? What's the order? What's the truncation error for our 2-point formulas? The forward and backward ones, in particular the forward in this case. What was the truncation error? We go with h, right? If I'm trying to use information, if I'm trying to use extra information, do I want something that's going to give me the same truncation error? No, I want to make the truncation error get better, right? The whole point of using more information is to make more accurate approximations, right? There's literally no reason to use a formula involving these 3 things if the truncation error doesn't get better. Literally no point, right? I already have something that's O of h. Why the hell would I do another formula that's more involved that has the same truncation error? It makes no sense, right? So I want to make this O of h squared, at least, right? Okay, so let's think about how we can get to O of h squared. What has to happen to get to O of h squared, I should say, to figure out what needs to cancel, okay? All right. So let's look at this. This is the quantity that we're trying to approximate. When I solve for that, you have to divide by h, right? Okay, which means that we'll cancel off 1 copy of h, everything that's left, right? But no more, correct? Well, if I divide this only by an h, it leaves an h, right? That's not going to give me a truncation error of at least O of h squared if I leave that term over, right? So it's this one that needs to cancel. So the f double prime needs to cancel if we're going to get to O of h squared for the truncation error. Right? If that f double prime term is there, then h squared is there. If h squared is there, we're going to divide by 1h. I have an h there, and I'm stuck. I'm at O of h, not h squared, right? And that's useless to me. I already have an O of h formula. Why would I make a more complicated formula to get the same error? That's dumb, right? Let's do more work to accomplish the same task. All right? Okay. So those need to cancel. So what should we do here to make those 2 things cancel? Okay? And it's 4 times the first one, because the one's a 1/2 and one's a 2, right? So let's do f of x naught plus 2h minus 4 times f of x naught plus h. And subtract. Okay? Do you see why it's a 4? There's a 1/2 here, and there's a 2 there. So you need to make those cancel. Okay? All right. How many f of x naughts do you have? Let's go again term by term. I'll circle them around. Let's go term by term. How many f of x naughts do you have? -3. Good. Right? If I do -4 times the first one and add it to the second one, it's kind of like linear algebra problems, isn't it? Like you're row reducing almost. Right? Okay. Now let's go to the next one. What do you get here? -2. We get -2 f prime of x naught h. We've rigged it so the next ones cancel, right? These go away. And then the other stuff has at least h cubed in it, right? The things that are left over have at least an h cubed in it, doesn't it? Yep. So now when we solve, we will add the 3 over, 3f of x naught over, I should say. And divide by -2h, because there's now a negative on that f prime of h, f prime of x naught times h. And then what's your truncation error? So h squared. Good. And you'll find that formula in the book. But it makes, okay, so what the idea here again is we came up with some of our formulas to try to give us more information to figure out better approximations with bigger h's, if you will, right? Because again, if it's O of h, to get within 100th, I might need to have my h be 100. But to get within 100th for O of h squared, I just need to make my h within a 10th. I'm estimating because of the fact that it's really constant multiples and those things. But that's the idea, right? It's better to get within a 10th to get better accuracy than to get within 100th to get the same accuracy. Does that make sense? Does concept make sense about how we're creating these formulas? Okay. Well, all right, so we've done this a couple of ways now. We've come up with formulas that give us approximations for, pardon me, integrals, and we come up with formulas that give us approximations for derivatives. There just may be formulas that we can give us approximations for several things in terms of small quantities. Okay, so this is going to lead into a topic that we refer to as Richardson extrapolation. All right. So let's say that we have a constant k, whatever a value k is approximated with some phi of h plus something that's on the order of just h. And let's say I want to be lazy. I'd like to get an approximation for that same constant that's, say, O of h squared rather than O of h, but not have to come up with a completely new formula. Use the same approximation formula that I have, but make my error better. Okay? See what we can do. All right? So let's write this out, what this would mean. So let's say I have my k is some phi of h. Phi is just representing a function that is my approximation. Okay? So, for example, I'll write it on the board. If I was using my forward difference approximation for the derivative, x naught is given. X naught doesn't change, right? This would be my, this is my phi of h. That's the function I'm using for that approximation. Right? It's just whatever function I'm using for my approximation in terms of h, that's what the phi is representing. Okay? All right. So to write this out, if I write it this way, see, okay, so we have our phi of h, and we know it's on the order of h squared for the truncation error, which means the part that I'm truncating off is some power series at h, and the lowest power of h that I see is the first power. That's what that means, right? Okay, I want to try to make this O of h squared without coming up with a new formula. Same phi, same approximation formula, the same phi, but I want to see if I can make my truncation error O of h squared rather than O of h. Here's what we're going to do. In this case, let's think about having an actual honest-to-goodness function that we can plug whatever we want into rather than maybe data that's incomplete. Okay. Well, to do this, what we'll do instead is, if this is supposed to work for an h, it should work for an h over 2. Right? If I plug in h over 2, that's even smaller. I should have something that's even a better approximation, right? So I should have something similar that looks like the same k, and then I'm going to plug in an h over 2 for h. Now I said my goal here is to try to, pardon me, try to get an approximation that is O of h squared. If I want an approximation that's O of h squared, I want to make my h terms go away, right? So to make my h terms go away, let's multiply this one by 2 and then subtract up, okay? Well, if I do 2k minus k, I still get k, right? If I do 2 times the second equation and subtract down, I would subtract up to the first equation, okay? We agree? We'll have 2 phi of h over 2 minus phi of h. Right? And then the middle terms cancel. These go away. Right? And then we'll get, I'm going to write it as just another constant here. Let's say I have a b, I'll call it a b2 h squared, a b3 h cubed, and so on down the line, just so I don't have to try to simplify constants. We've rigged it so that the h's go away. Now if I use this, and I'll give it a new name, I'll call it, say, capital phi. That new approximation formula is O of h squared. It's in terms of the original approximation formula, right? But now it's O of h squared instead of O of h. Do we see it? So this is the starting of what's referred to as Richardson extrapolation. Let's do another one. Let's go to the next step. I now have an approximation that looks like this, right? Let's do the same trick. Say I want to go from h squared to h cubed. Do the exact same trick again. Okay? So let's write it out. We have K is equal to some capital phi of H. And then again, we've got these constants that are on the order of H squared. And do the same trick. Put in H over 2 again. Oops. I want to work off of this formula, and I want to try to make it O of H cubed now rather than O of H squared. So I want the H, if I want to combine these two things again together, I want to combine them so the H squareds go away. What do you think we need to do to combine them? Much like what we did in the previous part. What do you think we should do to the second equation and then subtract off the first equation to make the H squareds go away? Multiply by 4, right? Because I'm going to over 2 squared, right? So if I do this one times 4 and then subtract up, we'll get a 3K on the left-hand side, right? Over here, we'll get a 4 phi of H over 2 minus capital phi of H. And then plus, I'm going to refer to them as C's now, a C3H cubed, a C4H to the fourth, and so on down the line. So this is now my new approximation. Oops, I guess I need to divide by 3 before I'm done. Our new approximation is the 4/3 phi of H over 2 minus phi of H, and then I got something that's on the order of H cubed. Now, I know I changed the letters, but I only changed the letters so that it wasn't going to get nasty. Remember that capital phi of H has been defined in terms of the original phi of H, right? The little phi of H. I haven't changed my approximation formula. I've just refined it a couple of steps, right? So I haven't created a new formula. I've used the old formula and refined. Now, I'm going to do something a little bit strange, but let's think about this for a second and then see why I'm going to write this a little bit strangely, if you will. The original one had a 2 that we multiplied by to get rid of the H over the 2 that was in the denominator for the H over 2. This one we multiplied by 4 to get rid of the 2 in the denominator for the H squared. If we wanted to do this again, I would need to get rid of an 8 in the denominator, wouldn't I? Because I have a 2 cubed in the denominator. Do it again and have a 2 to the fourth, and so on down the line. But each time I'm only subtracting 1, correct? So you're going to have a 2 to the n minus 1 term that's here, which ends up in the denominator. Okay? All right, so anyway, let's write it this way. I'm going to write it as a phi of H over 2. And then you'll have a plus 1 over 3. Oh, I forgot my 1/3 here. I forgot to divide my 3 all the way through. There should be a 1/3 in front of that. Sorry about that. There should be a 1/3 in front of that phi of H because I had to divide by each term by a 3. It's okay, when I was writing stuff out, preparing for class, I did the exact same thing. Well, at least I'm consistent. All right. So there's a 1/3 there. This 3 again is 2 squared minus 1. This 2 is the O of H to squared. That 2 is the same as the O of H squared part. Okay. So if you did it again, well, let's write it this way. Let's write it in general. if K is, I'll call it a little phi of n, I'll go back to a little phi of h plus O of h to the n, whatever that phi is, then I get the same pattern. I'll have a phi of h over 2 plus 1 over 2 to the n minus 1. Phi of h over 2 minus phi of h is, I'll write it approximately here, is O of h to the n plus 1. So this is what the Richardson extrapolation formula is. It's not restricted to just derivative formulas. It could be any approximation that we have that's in terms of h. Okay? So it could be an integration formula. It could be a polynomial interpolation formula. It could be whatever. Okay? All right. So let's do a quick example here in Excel to see how this would work. All right. So all right. So let's say, I know I got 3 minutes. So we'll see. Let's say I wanted to approximate. Let's say I wanted to approximate the derivative of cosine at x equal to 1 using our forward approximation formula. Okay? So okay. So say we want to use our forward approximation at 1. Okay? All right, so let's just put in some h's here. Now remember, at each stage, we're going to divide the h in half. So let's say I'll do a 0.1 for my first h, and then I will just take the previous h and divide it by 2. And let's go down a couple spots. Okay? Yeah, that's all right. I can make this a little bit faster, but I'll just type it in. All right, so I want to do forward approximation. So I'm going to use my h to start with. So remember, forward approximation is f of 1.01 minus f of 1 all over 0.1, right? Or for whatever the h is, correct? So for this first one, we'll just do cosine of 1 plus my h is up here, right? Yeah. Minus cosine of 1, and then all over the h that's up here. Right? So that gives us our forward approximation formula. We agree? We hit enter. I copied that down. The first one gave us for h equal to 0.1. The next one is 0.05. The next one is 0.125. All right. Now I have new approximations in terms of those h's. If I want to have them, I can use these as my new approximation functions. Okay. All right. So here I can use my new half the approximation, and then I'm not saying it very well. All right, when we went to O of h squared, that was what we came up with for that first step, right? It was 2 phi of h over 2 minus phi of h, split into 2. So this is basically 1 over 2 to the first minus 1 out in front. Just writing it in terms of the formula. All right, so this should be that, and then actually it's 2 times it, so it's just that minus that. Oops. That's the extrapolation formula for the first step, to go from O of h to O of h squared. And then copy that down. Now I can do it one more time. The next one would be what? It would be 2 squared minus 1 phi over 2 minus phi of h over 2 minus phi of h. Right? So the next one would be this one plus 1/3 times this one minus that one. And if I had another point, that I would do another step, but at this point we get to here. Now I've got something that's on the order of h cubed, right? Just by doing those formulas, I didn't have to create a formula. I just iteratively did this as I went down. And if I do negative sine of 1, which should be the actual derivative value, right? We got something that's pretty darn close. Just by iteratively going through the approximations that we had before. Notice that using the original formula, what was the best we got was negative 0.848, right? I didn't change the approximation formula. We just iterated through this extrapolation process and got an approximation that's correct to 5 decimal places without coming up with a new approximation formula. That's the extrapolation process. I'll create a video for this so you can see it a little bit better and post it on Moodle for you. Okay? I know that was fast at the end. So we'll create a formula, and we can see how to extend it pretty quickly then too if we have it in Excel. And then you should be able to think about how you could write a program as well. Okay. Have a good one. We'll see you on Thursday. Sorry about keeping you a couple of minutes late.